also in Politecnico di Milano.
Yeah.
And yeah, Marco is going to talk to us about many phases of heterogeneity. So let's just hear from him.
Yeah, thank you. Thank you for the introduction. Thank you for inviting me here. It's a great honor to be here together with all of you. Yeah, I'm going to talk about many different works today, and works that I've done in collaboration with some of the students that when I was in Turin, some ideas that I'm developing now with Colin as well. I just wanted to make a disclaimer. I'm not an optimization researcher like any of you here. I don't know why I'm presenting today. But my background is mainly in deep learning, and my research is focusing on transfer learning across different data sources and tasks, and I'm particularly interested in collaborative learning and modular learning. So my goal for today is to show how different practical settings share same underlying problems. That is why we are all here today, which is basically we are learning from heterogeneous sources under different constraints. And the easiest thing possible that we all know is you have a single source. So you train for a bunch of steps, and you have a model that is trained on a single source. You can do that for many others, but this is kind of unsatisfying, especially nowadays, where we're trying to train models on a bunch of different sources coming from, for instance, language models. We train models that are able to do coding and chatting with us, do mathematical problems, are multilingual. And this is already a challenging problem that is, we need to balance across these sources. We need to find optimal data mixtures, and exploring this, the Pareto front, and doing this is expensive. So this is a very difficult problem. We have people working on that. But we cannot always access all of these sources simultaneously. There are some constraints on data access, and different constraints give us different settings. But there are some critical challenges that are shared across them. So one setting that I worked on was continual learning. And in this case, you have a heterogeneity across time. So basically, you observe one sources at the time. You don't have access to past data. This is sequential training, and you only can train on your current data or task. The key issue here is that the model, when you move from one sources to another, the catastrophically forgets about what it has learned. This is just, you train on, for instance here, trivia QA, and then you forget about natural questions. And what you will really have to, what we would like to have is some model settings that is able to maintain this performance. Federated learning instead, we all know it's a heterogeneity across space. You have different data sources, but you cannot access all of them together because you have privacy constraint, and you want to train independently and have, because you have a communication constraint that you want to achieve. So you don't want to waste too much time communicating across all of this. So you train in parallel and you merge models. This causes the client drift problem that we all know. The local models overspecialize on client data, diverging from global optimization goal. And this is an issue that if you put together with something else that is partial participation, you have a spatial and temporal heterogeneity, because you observe only parts of the distribution here, and then you move on and you observe other parts of clients, so other parts of the distribution. So this induces some kind of a sequential learning problem as well. And at each round, the model gets biased towards most recent data. So it could forget some knowledge when you go from here to here. In fact, if you think about it, and you have only one client per round and no clients revisit, this is kind of the same problem of continual learning that you had before. The problem in federated learning is that when you have all of this issues, then you will have a slower and a noisier convergence optimization process, so you actually require much more communication, and we all know that. Now, if you add another constraint, that is, you don't have the possibility to do multiple rounds of communication, what you will have is something that nowadays is called model merging, which is combining different models that have been trained completely asynchronously across different data sources. So you have a single model aggregation, just kind of a federated learning, but in one step. And you have two core operations here: local gradient descent, optimize on different individual sources, kind of minimizing partial objectives. It's not the same. You don't have access to the full distribution, so you don't optimize for the global distribution. And then you have model aggregation, which combines these independently trained models in the parameter space. And these have two failure modes, which is, for the first one, you forget past knowledge, you get biased towards local data, you drift from the global solution. And in the model aggregation, you have interference from conflicting parameters that have been optimized for different goals. If you combine these two, you have different paradigms that suffer from different combination of these problems. So you have similar problems, maybe you will use similar solutions. For example, here, you can have a local train. You have the example of continual learning and federated learning that uses both the same technique, which is using optimization with proximal terms. So you don't want to, you add the penalty, you don't want to move from the old model here, and this is called, and in particular, you use Fisher information to weight these parameters, and this is called elastic weight consolidation in continual learning. In federated learning, you use FedProx, for instance, which is mitigating the client drift from the global model. You're just trying to stay close to the global model when you do local optimization. So this is just to give an example. Let me give an example of something else that I've done with one of my students. And for instance, in continual learning, we can define the problem of learning across different data in different orders, as you have a data set, and you have a function that gives you some schedules. So the data can be split in different chunks, so there can be different orders. And what you like to have is something that is an algorithm that is kind of robust or invariant to all of these schedules. So we can restrict ourselves to a specific class of predictors, like this one versus all predictors, and cheat a little bit and use a pre-trained model here, so that we can use something that is not continual learning at all. Is just you have a closed form solution for this, and you can use an exact online update here, so you can recover exactly the same closed form solution, so exactly the same predictor, and you can learn in time here. So this gives you a model that an algorithm that is exactly the same. That gives you exactly the same predictor, independently of the data stream, and of course, this is a little bit unsatisfying because you'd like to update also the representation. So you can do this by using a replay buffer. And if you construct the replay buffer in a certain way such that it's balanced across all of these sources, then you don't have any more issues with heterogeneity because you're not updating, you're not doing local training basically on a single source, but you have local training, you have training across all of these sources. And this is effectively a very strong baseline. So the reason for this is showing that it works really well compared to all of the other continual learning algorithms that instead are pretty, they have a high variance depending on many different schedules that you could have. Now, the same framework can transfer exactly to federated learning because you can see schedules as client splits. So if you adapt this online training procedure and you move, you use this ridge regression online formula on the clients to collect these statistics of the covariance matrix and the matrix B, then you can just communicate this on the server, and the server aggregates them. So, and when you have seen all of the data, then you will have exactly the same solution of the centralized problem as if you have seen all the data at once. And in fact, if you compare the performance of a linear probing, so you train the classifier with federated learning here, you will, and you compare it to the ridge regression online that we call Fed3R here, after that you have seen all the clients, then the performance are pretty different. So here we start from a pre-trained model. We apply this Fed3R solution here. You observe all of the clients. And here we observe the same number of clients, but the gradient-based solution is pretty behind. And here we have different level of heterogeneity, and it's basically how many clients you have split the data, and you recover exactly the same solution here of the centralized problem. You can use this to accelerate the performance of a gradient descent. So you use that as a solution, as an initialization. And then you keep doing, you apply federated averaging on top of that. So here I have three different scenarios. One, when you only fine-tune the classifier, which you see that it's not very good. Like you lose performance because heterogeneity is still there, and you don't have a solution for an algorithm to solve the heterogeneity problem. But if you fix the classifier, you see that you can actually pretty much train, and it works. So kind of give an hint that the problem is in the classifier. So learning a classifier in heterogeneous setting is pretty hard. So I know that we avoided the problem here. We bypassed completely the issue of gradient-based learning in heterogeneous settings. We have used an exact classifier aggregation formula, and we use a balanced buffer for continual learning. So we kind of hide our head in the sand. And because of constraints, often we cannot use exactly the same solution across settings. For instance, we cannot really use the buffer in federated learning because we cannot aggregate all the data. But we can transfer some similar ideas. So what we were thinking is, let's try to correct the local update by mimicking the centralized update, which is something that a lot of people also in this room probably did. We have algorithms like scaffold, mime, all this kind of stuff. And so we try to use momentum for solving this issue in federated learning. In particular, in the case of partial participation with data heterogeneity. And in that case, the heavy ball formulation here, when you have partial participation, is pretty biased. So this one is this momentum update is biased towards the client sample during the last round. So what we come up with is an idea that is, instead of using only the last update, we use a heavy ball formulation that takes into account a much larger window, which is why we call this generalized heavy ball momentum. And in this difference between tau, in these tau rounds of optimization, there's basically inside gradients from the past tau rounds. So we can use this to correct the bias that we have in the optimization. And if we use this in the client update, and we use this to inject some global information to the local optimization, we can guide the training towards a global solution and reduce the client drift. And this, in fact, accelerates quite a bit from, in the heterogeneous case, from tau equal to 1, which is the classic client level momentum. And we can see that if we use a larger window, especially the the optimal one is 1 over the client participation rate. It gives you very strong acceleration, similar to the convergence rates of the full participation case. Actually, we proved that for not through partial participation, but for cyclic partial participation, because, but that in this specific example here, this is uniform sampling, and it works pretty well. Actually, we compare it with different data sets, and on different data sets and in different architectures, and it's a pretty strong algorithm. Now, so basically we have some ideas that we can reuse across different settings. But so far we mainly discussed about the local training. What about the model aggregation? So one very successful technique now that they've been using nowadays for aggregation of the models of different models is model merging. And model merging combines experts that have been trained on different data. So, but the caveat here is that you have to start from the same pre-trained model. So you can we have a NeurIPS tutorial we had the NeurIPS tutorial this year where we cover many different methods and all the foundation for this particular setting. And but the important bit here is that you have to start from a model that has been first pre-trained on data. And the core operation is always the same. When I presented this at NeurIPS, people were like, oh, you're just doing averaging of the weights. In this room, I'm happy that you're not kind of baffled from this. And in fact, you can use this as a very simple tool for merging models. And you can also see that from another perspective that federated learning knows very well, which is we can consider the difference between the specialized model and the pre-trained model as a pseudo-gradient. And we can combine this pseudo-gradient together that they call task vectors and do it in a single round of aggregation, single round of federated learning. And one of the motivation for this is that multitask or multi-source learning is very expensive in terms of finding the optimal data mixture. So instead of training many different models, especially for the post-training pipeline, instead of trying different data mixtures, what they do is, because this is expensive, you need to retrain a model every time. What you can do is instead have different teams that work asynchronously on improving specific capabilities, and then meet together and cheaply explore different trade-offs post-hoc. So, for instance, this is an actual pipeline that is from the Common A paper from Cohere, where they repeat this merging technique in two phases. The first one is they do supervised fine-tuning, and they have different capabilities here. For instance, they train multilingual experts, coding experts, safety experts, and then they merge the checkpoints. They find the best checkpoints by evaluating the models, and then they move to the next stage. There is reinforcement learning, and they do exactly the same. A caveat here is that here you have a full control over the data, so you're not exactly training in a full heterogeneous setting. So in all of this local training, you inject a little bit of data from the other settings. So this helps. And then in the end, they also have this polishing phase where they train all together. So this is mainly to this is a logistic problem that they solve with this setting of model merging. But in the reality, you can also think about having experts put online by different contributors that they train on their data. And this data you don't have access to. You only have access to the final model. And this is not absurd. This is not absurd. There are many, this is the kind of the Hugging Face hub. This is a visualization of the Hugging Face, of the models on the Hugging Face hub. And all of these blue ones are kind of models that have been merged, moving from one other, starting from other models. So in this setting, however, independently fine-tuned models interfere when they are combined. There are several heuristics that can be used to improve the aggregation phase and reduce interference. And one, for instance, is this, the ties merging, that resolve interference by doing some pruning and sign agreement. So they try to remove the parameters that are not important so that they might be redundant and conflict to each other, and then they decide the sign of the specific parameters by choosing the ones with the highest magnitude. And this helps a little bit. So if you have a different number of tasks, you can see that this particular technique helps a little bit with respect to ties merging, with respect to task arithmetic, simple task arithmetic. But these different merging methods that have been developed, these different aggregation methods, treat this compatibility across models as an afterthought. So they basically rely on post-hoc fixes. One question that we had was, how can we train models that are actually composable by design?
Marco, may I ask you a question?
Yeah, sure.
Maybe this is the direction you're going in. I just want to understand the progression of the last few slides. So
yeah.
The examples where merging was working well were when it's all coming from the same initial checkpoint.
Mm-hmm.
But then is there not a problem of interference in that scenario as well? Like, is it really possible for those teams to operate quasi-independently, or?
Yeah, it is still the case, but it's let's say it's easier if you have some overlap between the data. So my point here is that it's still possible to train different models. In this particular setting, you are in a simpler scenario because it's more control.
Start from the same.
Yeah, no, you always have to start from the same initialization. Because otherwise, if you start from different models, even if, let's say that they have the same architecture, but these are different models, then you have issues like permutation, symmetries, and all this kind of stuff. In this specific case, you don't have this problem.
And the next slide, though, so what was the difference between this?
The difference is that here you don't know anything about how these other models are trained. You don't have any control, and you don't know. You cannot kind of decide how these models can be trained. You just assume, okay, someone gave me the models.
Okay. So we know that they also, here everything started at the same checkpoint also.
Yeah, they also start from the same checkpoint.
What happened in between and the final?
To be honest, I'm not entirely sure if this all starts from the same checkpoints, because sometimes merging on Hugging Face is quite nasty. Yeah. They just use, merging means that we took some layers from one models and we put another models together, and then we train for other iterations. We keep training. So this is a motivating example, but inside of this, there are some cases for sure where they start.
Understand the difference between
No, yeah, sorry. Hope that's clear now. So how can we train models that are composable by design? This slide is mainly about connecting to other works, which is, other people are trying to think, how should we train this model to be more mergeable? And they discovered that, actually, if you train your best experts ever, so this one is just the full fine-tuning of the experts, the average performance of the single experts. Then when you merge them, actually, after some point, it's harder to merge. And this is because these are pretty good experts, but they overspecialize. So overspecialization could hurt aggregation. It's kind of remind me about the client drift, all these kind of issues that we have discussed already. So kind of, again, people are rediscovering the same things under different circumstances. So how long do I have? How much do I have?
It's like 5-ish minutes.
Okay, all good. So let's start with this motivation that is a property that we would like the models to have. So we like to have the models that are behaving in such a way that are independent. So whenever they activate, when they're merged together, they need to activate only when they see, when you pass some data for that specific task vector or that specific model. And we can formalize this property and derive some kind of a fine-tuning update that approximately satisfies it when the models are merged. And basically, this is kind of a, you can think about it as a piecewise linear function, piecewise functions here. And yeah, and basically you want the models to be, if the data are not from any of the support, you want to behave exactly as the pre-trained model. Otherwise, you want to activate only if the data are from this specific task. And if you linearize it, and then you see that basically you want this to be different, equal to 0 for all the tasks different from t. Basically, we want this to be active only for the specific x for this specific data set. And to satisfy this constraint, actually you can do it, but you need the access to the data of all the other tasks. That is something that we said we don't have. But what we discovered empirically is that, and basically this, we can, sorry, maybe just one step. We found that this constraint here, which is basically the parameters of the gradient of the parameters of the original model. If we look for the parameters that are close to 0, so that we can make this close to 0 by this multiplication, basically we discovered that it doesn't matter what data do we use for this. It doesn't matter. The performance are always the same. So if we prune by using data from other tasks and then evaluate, we'll see that it doesn't matter which data we computed the mask, which data we use to compute the mask. So we can prune this data, we can prune these parameters, and it doesn't matter because which data we use for that. Sorry. So we can kind of derive a sparse fine-tuning rule that approximately satisfies this constraint. And the main idea is that we want to update only the parameters that have very low gradients. And we can use the data from the specific task that we are optimizing to compute this mask. And in the case of nonlinear fine-tuning, if we optimize for a specific task, then we lose performance on the others. In this specific case, if you fine-tune only these specific parameters that have a low gradient, then the performance on the other tasks remains the same. And this, when we put together, we have higher, when we merge the model together, we have less interference. And especially, basically, it reduces interference when merging and better retains the individual performance of the models. It's better than using just post-hoc aggregation methods. Okay, just a few takeaways. I think I have said all I wanted to say. Learning from different sources presents shared challenges across different settings. Depending on the constraints, we can focus on either improving local training, aggregation, or both. And these methods can be transferable across settings. And I do believe that sub-communities should collaborate and find a unifying framework that could accelerate research and prevent redundant efforts. So what's next? I have some meta questions that it would be nice to chat with you together during these days. So how do large pre-trained models transform our approach to data heterogeneity, for instance, so that we can build more modular models? Because we have seen that in the single aggregation setting, like model merging, we can do stuff that probably weren't possible without pre-trained models. So in that case, data heterogeneity was, before it was a crux, now maybe it's something that we can exploit to create better training. And how can we automatically determine when we can compose and transfer across different sources, and when, in which cases are instead harmful? Another question that I have, and I'm working on these days, is when should we prefer merging over other other techniques like parameter isolation methods, so that, mixture of experts or routing of different experts? Because, again, to my point here, maybe composition and transferability is not always possible. And there might be cases to reach better trade-offs just by simply using different models instead of trying to put all the sources together into a single model. I think that's it. That's all I wanted to say. Thank you so much.
I have one question. Yeah.
Question. So my question is about the Fed 3R method that you mentioned. Can you give some intuition about why it works so much better than the standard Fed averaging and other methods? Is it because it's for like a linear problem?
Yeah, basically here we're not using gradient descent at all, because we're using this aggregation. It's basically just, that the solution in this case is the solution of a ridge regression. So it's this one. And we can use this online update by, collecting this on each client and then sending to the server, and then it's...
How do you know that it is the solution of a ridge regression problem?
This and this?
Yeah.
Oh, it's...
That's just the way the objective function is defined.
What do you mean, like... yeah, this is... Sorry, this is...
Okay, I see. Yeah, I think I missed that.
So basically you send the problem to the server, and the server solves the problem, right?
Yeah.
All the clients send the problem.
You send the statistics here that are just basically the aggregate. You aggregate this, you build this incrementally, and then the server just solve it. Yeah, it's kind of a bypassing the problem, but it works really well in practice. So this is a kind of a I'm using iNaturalist here. It's pretty hard. It's a pretty realistic problem. So I think it's and the nice thing is that here I presented it as a kind of a synchronous synchronous algorithm. Like I see 10 clients at the time, but in principle, I mean, you don't need to wait. It's not the sequential learning here. Like you can just say, okay, whenever all the clients can communicate to their statistics, then I can start the federated learning afterwards.
So the kind of block that I would love to see
Yeah.
is assigning some cost to the workers,
Mm-hmm.
and then to the communication and to the server,
Mm-hmm.
and showing the total time in that cost model.
Uh-huh.
Because these methods have very different patterns, with very different costs
Yeah.
in this model.
Yeah, we have something on the paper, like from a communication perspective. But the computationally wise, is that what you mean? Like you?
I mean all three, because for instance, your method offloads a lot of work to the server.
Yeah.
Where at federated averaging, there's just simple averaging going on, but you have linear solve,
Mm-hmm.
right?
Yeah.
So that costs something.
Oh, yeah,
but
yeah,
this
for
one
sure.
hides it, right?
Mm-hmm.
On the other hand, there's some smart things about this. So So the full picture, I don't see the full picture.
Okay. Yeah. Yeah, it's a good point. Yeah, for sure. We can chat offline about that. I'm happy to do it. Okay. Thank you.
Now we have the break, right?
Yes, now we have the break, yes. And I think it's actually tea time at 3 on the second floor. If you want to pop up there for snacks, I think is it? I think there's snacks there, yeah. But 3:15 is the next talk.